Hello students and welcome to part 2. Let's continue to describe discrete graphs, which are unconnected graphs, and looking at the situation with Simon. In this situation, we know that the domain cannot be any number. The domain can only be the whole numbers from 0 to 10 because Simon must sell a whole candle. The candles do not come in any number other than a whole number. Likewise, the range will be every $2.5. So in other words, he can only get earn $0, $2.50, $5, $7.50, $10, up to $25 for his school. So this would create a distinct graph because if he sells 0, he would get 0. If he sells 1, he would get $2.50. If he sold 2, he'd get $5. If he sold 3, $7.50, and so on with distinct unconnected points because the domain and range could not be a range of numbers, but rather distinct types of numbers. Now, the other type of graph is continuous. So here's a situation that would have a continuous or connected graph. Tina's heartbeat is being monitored while she exercises on a treadmill. While walking, her rate remains the same. As she increases her pace, her heart rate rises at a steady rate. When she begins to run, her heartbeat increases more rapidly and then remains high as she runs. As she decreases her pace, her heart rate slows down and returns to normal. So as we think about our independent and dependent variables, we're saying that her heart rate depends on the time that she's been exercising. Now, if you think about heart rate is always occurring. Whether she's exercising, whether it's being monitored, it is a constant occurrence. And that means that her heart rate will always be monitored. Likewise, time is always occurring. So this will be a continuous graph because the heart rate is continuously being monitored while she exercises, and her time is constantly occurring as she exercises. So if we pull out our important information, we can create a connected graph to represent the time and the heart rate. So it says Tina's heartbeat is being measured while she exercises on a treadmill. While walking, her rate remains the same. As she increases her pace, that's talking about pace, her heart rate rises at a steady rate. When she begins to run, her heartbeat increases more rapidly and then remains high as she runs. As she decreases her pace, this decreases is referring to the pace, not her heart rate. Her heart rate slows down and returns to her normal rate. So, if we think about it, we don't want to start here at 0 because we don't want her heart rate to be 0. The time, however, can be 0 to represent the initial amount of time or the initial starting point on the treadmill. So it says that her heart rate remained the same, so we'll go straight across. And then as she increased her pace, her heart rate rose at a steady rate, so it slowly went up. But then as she started running, it increased more rapidly, so get a steeper line, remained high while she ran, and then slowed down to her normal rate. This graph will be continuous because heart rate and time are always occurring, and this is how her heart rate changed while she exercised. So let's tell whether each graph would be continuous or discrete and make a sketch for the situation. So it says Henry begins to drain a water tank by opening a valve. Then he opens another valve. That's going to make the water come out twice as fast. Then he closes the first valve, so it's only going to go out half as much like it did at the beginning, and he leaves the second valve open until the tank is empty. So in this problem, we're comparing the amount of water in the tank to time. Our independent variable is time because the water does not affect time, but time affects the water. And our dependent variable will be the amount of water in the tank. We will continuously be able to measure time, and we will continuously be able to measure the amount of water in the tank. Even when it's empty, we can still measure that the tank is empty. So our y value is the water, and our x value is time. Now we're going to start our graph up here because at the beginning it had lots of water in it. And then it slowly began to drain. When he opened the second valve, it drained more quickly, so we're going to drop even faster. But then he closed that second valve, so we're going to go back to this same slant from one valve until it's empty, which is when it reaches the x-axis. So this would be how the water would drain out of the tank. Let's look at another example. It says, Jamie is taking an 8-week keyboarding class. At the end of each week, she takes a test to find the number of words she can type per minute. She improves each week. Well, we know she's improving, so that the relationship is going to be going upward. Now, think about what we're comparing here. We're comparing the week, the end of the week, or one test. Okay, so week number to the number of minutes, number of words she can type each minute. The number of words she can type each minute depends on the week because she's getting better each week. Now, even though week is a measure of time, in this case, Jamie is not being measured during the entire week at every moment. So this is only going to occur in distinct points because she's only getting tested once a week. So we're going to have distinct points, 8 of them because she's going to be tested each week. And we don't know exactly how good she is, so I'm not going to label numbers on this side, but I'm going to put WPM, which is a computer way of saying words per minute, kind of like MPH, miles per hour. Now, we don't know how good she was to begin with, but I'm sure she could at least type a word per minute, so we're not going to put it here like she couldn't type anything. So we'll start here and just show week 1 she might have been here, but week 2 she got a little better, and week 3 she got even better than that, and we'll just show the dots increasing over time. But this will be a discrete graph because she is not continuously measuring her words per minute at every moment during the week. Now, you can also reverse what we just did. I gave you a situation and you had to come up with a graph. But you could also take a graph and try to figure out what you think the situation might be. So for example, this one might actually be a person's bounce height on a trampoline. So here they are, they're touching the trampoline, they jump up. They stay in the air for a second and then they come back down to the ground. And you can imagine if this was a trampoline, it would probably repeat itself over and over. Here's a discrete graph. Maybe this represents the number of items you sell in a fundraiser and how many prizes you get. So maybe if you sell one item, you get one prize. If you sell two items, you get one prize. If you sell three items, you get one prize. If you sell four items, you get one prize. If you sell five items, you get one prize. But if you sell six items, you get two prizes, all the way up to 10 items, still getting two prizes, and then every set of five increasing by one prize. And that's not the only situation this graph might represent, but just one way of looking at it. So let's summarize what we've learned. We've learned that there are two types of graphs that we can make. We can make a continuous graph or a discrete graph. We also learned what categorizes each type. A continuous graph is made of connected points, whereas a discrete graph is made of unconnected points.